Theoretical developments suggesting that a warp drive powered by conventional fuel types might be possible have led to a noticeable increase in the number of scientific papers on this topic. Among these studies, one of the most striking explores what could happen if things go wrong during a warp drive journey. For example, if the drive collapses or explodes. Get ready, because today we're going to simulate the collapse of a warp drive based on a scientific paper. The warp drive, or warp bubble, is a hypothetical technology that could open the door to faster-than-light travel in space. However, it's important to note right away that this speed exceeds the speed of light only from the perspective of outside observers. The core principle of the system is that it compresses space-time in front of the spacecraft while expanding it behind. That's because, while nothing in the universe can exceed the speed of light, space-time itself can expand or contract, and this change is not subject to any speed limit. This enables a spacecraft equipped with a warp drive to traverse distances in less time than light would, without violating Einstein's cosmic speed limit. For those interested in the physical foundations and technical details of the warp drive, you can find our dedicated deep dive video linked in the description below. Warp drives are theoretical engines that are assumed to bend space itself using massive amounts of energy. The entire Star Trek universe is almost entirely built upon this technology. If you're dreaming of an intergalactic empire, owning a warp drive is practically a necessity. The working principle of these engines is quite dramatic. They compress the space in front of them and expand the space behind, effectively bringing the destination closer. This process occurs only in a limited area around the spacecraft, roughly the size of a bubble. Instead of affecting all of space, it only manipulates the local spacetime. Therefore, in theory, it is expected not to cause harm to its surroundings. However, whether this holds true in practice remains unknown. And this is exactly where scientists have turned their attention to what might happen if a system that bends spacetime with such intense energy malfunctions or collapses. Just like a massive ship sinking can create waves that overwhelm smaller boats nearby, a collapsing warp drive could emit high-energy gravitational waves in all directions. A newly published scientific study has, for the first time, examined in detail the cosmic impact such a collapse could unleash. Gravitational waves are ripples in the fabric of spacetime and are usually formed by highly energetic cosmic events, such as black hole or neutron star mergers. But these waves can also be emitted from systems with exotic spacetime structures, not just from known celestial bodies, such as wormholes or warp drives, which remain theoretical. You can think of it like a massive ship plowing through the ocean. No matter how far away the ship is, the waves it creates eventually reach the shore. Likewise, a warp drive-equipped spacecraft that bends space as it moves will inevitably generate gravitational waves. In recent years, advanced gravitational wave detectors have been developed not just for identifying astrophysical events, but also with the potential to detect traces of warp drives, if they exist, used by other civilizations. With this possibility in mind, several research groups have already launched projects aimed at analyzing such signals. Warp drives operate by bending local spacetime, depending on the size of the ship and the level of energy used, and during this process, they emit gravitational waves into their surroundings. First predicted by Albert Einstein within the framework of general relativity, these waves were directly observed for the first time in 2015 by the Advanced LIGO detectors. This observation was a remarkably sensitive achievement, detecting ripples caused by the merger of two black holes millions of light years away. Therefore, if a warp drive were to collapse, we have now reached a point where its effects can be modeled and evaluated with scientific accuracy. Under normal conditions, a warp drive operating at a steady speed does not produce gravitational waves. However, when the drive collapses, accelerates, or decelerates, these dynamic changes inevitably generate gravitational waves. Taking this into account, a team of physicists from Queen Mary University of London, the University of Potsdam, the Max Planck Institute for Gravitational Physics, and Cardiff University decided to investigate a warp drive collapse scenario in detail. Now you might wonder, why would so many scientists study a warp drive collapse when no such drive has been built yet? As we mentioned at the beginning of the video, humanity hopes to one day detect other intelligent civilizations through the gravitational waves produced by their technologies. If gravitational wave detectors pick up a massive signal in a region where there are no black holes, supernovae, or neutron star explosions, there's a strong possibility that it originates from a warp drive. This study aims to calculate just how far away the gravitational waves from such a warp drive could be detected. In doing so, the team also evaluated the potentially catastrophic side effects such a collapse could produce. The scientists began their study based on a warp bubble originally defined by Alcubierre, assuming that this bubble has a constant wall thickness. Miguel Alcubierre is the theoretical physicist who first proposed the concept of the warp drive in the 1990s. Using his definition as a foundation, the researchers created a model of a space-time bubble with uniform thickness. You can imagine a warp bubble as a soap bubble shell surrounding a spacecraft. Inside the shell lies normal space-time, while outside, space-time is highly distorted. The distance between the inner and outer surfaces of the shell is referred to as the wall thickness. Keeping this thickness constant, meaning the same in all directions and times, likely made the calculations much more manageable. In reality, it doesn't have to remain constant, but for a stable and smooth journey, it is preferred to be so. Building on this definition, the researchers developed a formulation to understand how the so-called warp fluid behaves. The term warp fluid does not refer to any real substance, but rather to a theoretical construct that represents the energy-momentum distribution required to bend spacetime. The spacecraft inside the warp bubble sits at the center of this hypothetical fluid. The warp fluid compresses spacetime in front of the ship and expands it behind. This is what leads to the formation of the warp bubble. If you imagine spacetime as a stretched fabric, the warp fluid acts like an invisible pressure field, pushing down on the front of the sheet and pulling it upward from the back. In essence, it is the enormous energy density caused by this fluid that bends space. You might ask, so how exactly would this engine collapse? Let's break it down step by step from the beginning. In the study, the warp bubble considered has a diameter of 1 kilometer, meaning spacetime is being warped within this scale. The target is Proxima Centauri, the closest star system to Earth, located about 4 light-years away. The spacecraft itself is quite small compared to the massive warp bubble that surrounds it. According to the scenario, a launch pad is established on the surface of the moon. A 3-person crew board the spacecraft equipped with a warp engine. In the moon's low-gravity environment, plasma thrusters beneath the ship are positioned for vertical takeoff. The commander completes final checks on the flight computer and gives mission approval. The warp engine is initially programmed to operate at a constant velocity, but balancing such intense energy isn't exactly easy. If any error occurs, or the engine loses its stability, the uncontrolled warping of spacetime makes a system collapse inevitable. T-0. The plasma thrusters engage with a subtle vibration. Ionized gases burst from beneath the spacecraft, kicking up gray dust clouds across the moon's surface. The ship rises slowly but steadily, climbing toward its pre-designated orbital altitude. Once it reaches orbit, the warp drive ignition sequence begins. At the heart of this system lies a theoretical energy field used to bend spacetime, the so-called warp fluid. Though invisible, this fluid is generated virtually within the system and dynamically configured to compress spacetime in the front while expanding it at the back. The distribution of the fluid is calibrated to form a warp bubble around the ship, locally altering the structure of spacetime. As the simulation begins, magnetic fields surrounding the engine start to oscillate. Inside, the crew feels no motion or tremor, but external sensors indicate that the geometry of spacetime is beginning to bend slowly. Once the commander confirms the main warp trigger, the system enters its final phase and the warp engine activates. From that moment forward, the ship remains stationary within its own local spacetime, while the warp bubble folds the surrounding spacetime and propels itself forward. To an outside observer, the spacecraft would appear to change position instantaneously. A journey to Proxima Centauri that would normally take 4.2 years at the speed of light is completed in about 4 minutes, thanks to the bending of spacetime. The most accurate analogy for warp travel is this: arriving before light, without traveling faster than light. Let's be honest, this is a technology that completely overturns our classical understanding of time and space. But when we return from the journey, we realize that it's not just the laws of physics that have been flipped our understanding of technology has too. Only 45 seconds after the warp engine is activated, a warning appears on the screen. Warp fluid imbalance detected. We could see gravitational waves rippling through space-time like massive ocean waves. The warp engine was collapsing. A ring of positive energy, generated by the unstable warp fluid, was expanding and heading straight toward us. From this point forward, no recording device or human witness would remain to describe what happens. And so, we continue with the rest based on the scientific paper. The paper emphasizes that a warp bubble becoming unstable is highly plausible. The main reason is the razor-thin balance between positive and negative energy. Even a tiny external disturbance could disrupt it. For example, no matter how well the magnetic fields in the system are shielded, an unpredictable external factor, like a sudden solar flare, could destabilize the system and trigger the collapse. In the simulation, the warp bubble examined has a diameter of approximately 1 kilometer. If space-time bends at that scale and the system collapses, it would result in an extraordinary energy release into space. According to the study, the collapse of a warp bubble this size is comparable to the conversion of about 0.677 solar masses into pure energy. Using Einstein's famous equation, E equals mc squared, this equals approximately 610 joules, an almost unimaginable amount. This energy level is on par with, and in some cases may even exceed, the most powerful explosions known in the universe, supernovae. To better grasp the magnitude of this energy, let's make a comparison. This amount is approximately 10 superscript 3 times greater than the energy released by Tsar Bomba, the most powerful nuclear explosion in human history. Of course, since this collapse would occur in the vacuum of space, it wouldn't produce a traditional shockwave. Instead, it would generate extremely high-frequency gravitational waves within the surrounding fabric of space-time. According to the simulation results, these waves would have a frequency of around 300 kilohertz, propagating outward at the speed of light. This means that systems like warp drives could have profound effects on the universe, not only when they function, but also when they fail. According to the paper, the consequences of a warp drive collapse with a diameter of 1 kilometer would vary greatly depending on its distance from Earth. If the collapse occurs at an intergalactic distance, for example, about 1 megaparsec, or roughly 3.26 million light-years away, the gravitational wave signal would be significantly weakened, detectable only by extremely sensitive instruments. In such a case, there would be no physical damage on Earth. But if such an explosion were to occur on the Moon, the scenario changes drastically. Though it's difficult to predict precisely, let's apply a bit of scientific imagination. If the 1 kilometer wide warp bubble simulated in the study were to collapse on the lunar surface, the event would not simply be considered a technical malfunction. It would qualify as a planet-scale doomsday scenario. While the paper does not directly address this specific case, the energy values it provides, approximately 6 times 10 to the power of 47 joules, the equivalent of converting 0.677 solar masses into energy, show that such a blast would exceed even the energy released in a supernova. And this explosion would occur just 1.28 seconds away from Earth. Assuming a black hole or wormhole does not form as a result, the situation would unfold as follows. In an event of this magnitude, the gravitational waves radiating through space wouldn't merely stretch the fabric of space-time, they would nearly tear it apart, especially near the origin of the explosion. Earth's crust would not shift by millimeters, but crack on a regional scale in response. It is highly likely that microseismic discharge zones, unlike anything experienced in recorded earthquakes, would emerge on the surface. The tectonic plates beneath entire continents would accelerate to such a degree that mountain ranges could collapse in just a matter of minutes. But the most devastating consequence would be this. The incoming wave might be powerful enough to shatter Earth's magnetosphere. The planet's magnetic shield, our only protection, could be punctured by the high-energy particles released from the collapse. And this wouldn't be a temporary failure. It could mean the permanent collapse of the magnetosphere. Deadly radiation from the sun would begin to reach the surface without filtering. Within minutes, the upper layers of Earth's atmosphere would ignite. The ozone layer, under the intense bombardment of ionized particles, would dissolve. When the sun rises, death begins. To put it bluntly, about 12 minutes after sunrise, the civilization we built over thousands of years would vanish without a trace.